Right now, between two supernovae, space is quietly building planets. The loud moments make headlines, but the quiet time does the work. I mean the long stretches of slow change between cosmic fireworks. Those in-between years decide which stars form and which worlds appear. Think of it as cosmic scaffolding rising while the crowd looks away. It is the lull where hidden processes shape the next spectacle. You should care because those lulls write habitability and structure. Gravity sifts matter, gas cools, and chemistry clicks into place. Magnetic fields braid turbulence, while starlight sculpts the edges of clouds. Tiny pushes add up and the future quietly tilts. Whole galaxies drift, rebalance, and feed on barely visible streams. Black holes idle, yet their breath warms clusters across megaparsecs. Our sun rose from a cloud that cooled for millions of years. The Milky Way's bar slowly grew while no one was watching. Galaxies grow most between the headlines, not during them. One-sentence recap: the universe is busiest when it seems still. A cold cloud hangs between spiral arms, lit by a lonely star. This is downtime in the interstellar medium, patient and methodical. These silent grains decide which molecules assemble and how planets start. In plain words, dust specks bump gently, then stick because ice is glue. Frost layers trap water, carbon monoxide, methanol, and simple organics. Cosmic rays crack bonds, so reactive fragments meet on grained surfaces. Ultraviolet light breaks molecules, and darkness lets them rebuild again. Turbulence stirs pockets, so fresh gas meets processed mineral faces. In dense cores, gas shields itself, and cooling accelerates growth. Lab experiments show sticking peaks near -100 degrees Celsius. Simulations match, as micron grains grow faster when turbulence is mild. Picture the Taurus cloud, 10 Kelvin and 10,000 atoms per cubic centimeter. There, a micron grain can become a pebble in 1 million years. Comets inherit these ices, then deliver them to newborn rocky worlds. Stardust from older giants adds silicates that strengthen those icy crusts. Observers map methanol lines and watch chemistry thicken at filaments. That matters because these mantles set prebiotic inventories on day one. Net result: quiet cold chemistry writes the opening page of habitability. Far from any collision, a galaxy slowly rewrites its own shape. Astronomers call this secular evolution, steady change without a violent merger. It matters because bars and spirals redistribute mass and steer gas. Torques from the bar steal angular momentum from orbiting molecular clouds. Resonances trap stars and gently slide them across the disk. Spiral arms herd clouds, then trigger starbirth along glowing dust lanes. Meanwhile, the disk warms, thickens, and gradually builds a central bulge. Underneath, gravity and orbits quietly trade momentum and rearrange mass. Gas piles near resonances, then forms rings that light the inner disk. Star formation there heats the gas and helps the bar persist. Streams of stripped stars arc around the halo like faint rivers. They whisper that gravity is always editing, even on calm days. Look at NGC 1300, a grand bar stretching tens of thousands of light years. Its inner ring spans roughly 3 kiloparsecs, packed with young clusters. In the Milky Way, the bar funnels gas toward a few hundred parsecs. Over hundreds of millions of years, rings of star formation brighten there. A few percent of disk mass can migrate several kiloparsecs outward. So the picture is quiet forces sculpt galaxies between the crashes. Between galaxy clusters, the cosmic web threads matter along faint filaments. That flow is cold accretion, gas sliding into halos without chaos. You care because steady feeding controls how galaxies live and grow. Gas follows gravity, then compresses and warms near the halo edge. Shocks flare, energy spreads, and the gas settles into orbit. Some streams stay cool, near 10 to the power of 5 Kelvin. Those threads pierce to the core and form stars efficiently. Others stall, cool slowly, and drizzle into disks over long spans. Dark matter builds the scaffolding and sets the traffic pattern. Feedback from stars and black holes puffs, then recycles the gas. The tug-of-war regulates densities, temperatures, and metallicity in time. Simulations show filaments brightening as knots merge, then fading again. A Milky Way-sized halo gains a few solar masses each year. Over 1 billion years, that quiet trickle builds a massive disk. Dwarf galaxies feel bursts, but massive disks prefer steady meals. Observers find Lyman-alpha blobs that trace those inflowing pathways. Radio maps catch faint synchrotron bridges connecting clusters across megaparsecs. Rule of thumb: filaments are the supply lines between the headlines. Telescopes watch the quiet work, even when nothing seems to happen. Think of it like listening for whispers across a stadium. Hidden drifts decide the next bright event, so patience pays. Radio arrays map the 21-centimeter glow from cold hydrogen. They trace sheets and filaments that cradle forming galaxies gently. X-ray observatories catch soft Kev heat in cluster atmospheres. Those images reveal ripples, cavities, and long sloshing motions. Spectrographs read quasar absorption lines and measure slow metal mixing. Weak lensing maps mass by how it bends background galaxies. Pulsar clocks test spacetime ripples and reveal serene gravitational tides. Star surveys track subtle motions and expose long-term galactic editing. Gaia measures micro-arcsecond shifts and charts waves passing through our disk. Over a decade, that precision untangles streams, migration, and resonances. JWST images cold dust in star factories, even in distant systems. Combined, these tools build time lapses from snapshots taken years apart. Bottom line, instruments make stillness visible with ruthless consistency. Each small dataset adds a brick, then the wall appears. Quiet signals stack, and the universe tells on itself. After a supernova fades, its debris keeps working in the dark. This is the mixing phase, where elements join the neighborhood. It matters because those metals seed planets and feed the next stars. The remnant expands, sweeps gas, and forms ragged, fingered edges. Shocks heat dust, molecules shatter, then rebuild as the gas cools. Magnetic fields wrinkle the shell, and turbulence stirs heavy elements. The blast slows, fades, and hands energy to the wider cloud. Clumps overtake clumps, creating vortices that fold chemistry like batter. Radiation escapes, cooling accelerates, and grains regrow layered mantles. Cassiopeia A shows knots racing at 5,000 kilometers per second. Its shell spans about 10 light years after 3 centuries. In 100,000 years, the shock blends into the medium. Several solar masses of oxygen and silicon join future disks. Iron seeds cores, while carbon adds strength to icy crusts. Observers catch silicon monoxide masers brightening as dust reforms. Models show dust survival rises when clumps shield each other. The timeline is long, but the energy keeps paying forward. What to remember, the bang is brief, but the mixing lasts ages. Out near a cluster's edge, the atmosphere looks calm and blue. This is the intracluster medium doing weather, without any storms. You care because that weather regulates galaxy growth for eons. Ghostly sound waves ripple outward from a central black hole. Hot gas sloshes, trades heat, and spreads metals across megaparsecs. Gentle turbulence prevents runaway cooling and throttles starbirth in big galaxies. Thin magnetic fields guide conduction and tie distant regions together. Jets inflate bubbles which rise and stir like underwater balloons. The bubbles do work on gas, then fade into gentle eddies. Observers map ripples in Perseus as rings under frosted glass. Each ring carries energy equal to millions of supernovae, spread widely. Temperatures sit near tens of millions of Kelvin, stable for ages. Cooling times often exceed 1 billion years, even in dense cores. When cooling wins briefly, filaments condense and drizzle back toward centers. Then feedback wakes, reheats gas, and restores the slow balance. Simulations reproduce these cycles, matching sizes, speeds, and ripple spacing. The heartbeat is slow, yet it governs a whole city of galaxies. Net result, quiet feedback stabilizes clusters and sets their slow rhythm. At a galaxy's center, the black hole sits between bright feasts. This is the low state, where the engine idles for ages. It matters because faint feeding still shapes the halo around it. Gas drifts inward, loses heat, and radiates inefficiently as it falls. The flow puffs into a thick, dim, advection-dominated disk. Only a fraction reaches the hole, while most energy escapes outward. Modest jets thread outward and warm the surrounding atmosphere. Stars pass too close and donate wisps that keep things lit. Magnetic fields reconnect, launching flares that fade within minutes. Sagittarius A star flickers daily, yet averages a tiny appetite. Typical activity runs near 1,000th of the Eddington limit. M87's jet looks steady for decades in human time. Mechanical power dominates, doing heat instead of bright light. That energy couples gently, keeping cluster gas near a stable balance. Polarization maps reveal ordered fields inside a shadow sized by relativity. Timing studies find lags that locate the faintest parts of the flow. The brightest days pass quickly, but the baseline rules the decades. Bottom line, black holes govern quietly, long after the quasar era. So between two bursts, the universe quietly rearranges its future. We walk through clouds, galaxies, filaments, clusters, and patient black holes. The immediate takeaway is simple: stillness does the building while noise announces it. Our sun owes its start to that slow backstage labor. The next supernova's metals are mixing right now, far from cameras. Bars are steering gas tonight, moving stars by silent millimeters. Filaments are feeding halos steadily, like veins beneath dark skin. Cluster weather is pulsing softly, keeping giants from flaming out. Even black holes are humming, holding their cities in balance. If that changed how you see the gaps, stick around. I share space stories that favor clarity, evidence, and awe. Tap subscribe if you want more calm, science-heavy deep dives. Thanks for watching and for spending time in the in-between. Next time you see a headline, remember the rehearsal that made it.